Hi, I'm Randall Heyman, a mathematics academic, and this is my Corona Help playlist of my YouTube channel. If you'd like me to do a video for either you or your students or your child or your grandchild, and you think I might be able to help you with some mathematical problem or concept, well then comment below the video or send me an email. And if I think I can help you, I will try and do so. So this is part 5, the last part of showing that any integral domain, up here, any integral domain can be embedded in a quotient field. And we're up to the final step. We've shown that, what have we shown? Let's have a look back. It's getting late. We've defined how to create a set called the fractions from the integers. We've shown how to define two operations, here and here. Two operations for how the fractions can be added and multiplied. And we've gone through and shown that this field of fractions is in fact a field. So now there's this concept that the integers are embedded in the fractions, or the fractions, or the field of fractions contains the integers, or a quotient field is embedded, an integral domain is embedded in its quotient field. So let's try and put together some stuff here. I don't want to get too buried in the minutiae. I want to try and draw some pictures and explain what's the big picture here. So look, the first thing is that we're used to sort of putting this sort of thing. The set of integers is a subset of the, the integers are a subset of the rationals or the fractions. Now, we're being a bit vague here about whether we mean, do we mean just the set, or do we mean the whole concept of the field or the ring or the group or whatever it is. We've seen before that you need to really define a field or a ring properly, you have to specify the binary operations, not just the set. So it's true that the set of integers, so let's write something here. We could put it this way, what you probably used to, the set of integers is in fact a subset of the set of fractions. That's fine, that's not in dispute. That's an important part of making this embedding work, but there's a lot more, there's a few more things to it. So let's draw it, rather than draw it that way, let's draw it this way. So here's the set. Where am I going to put this? Here. Let's rub out this. Okay, so here we've got over here the set of integers. And down over here, we've got the set of fractions. And remember, as always, you can replace, if you want something more general, you can replace with this the set of the integral domain, and here is the set that's part of the field of fractions, if you want to take a more general approach. Okay, so let's have a think about here. Here's a point A, some integer, and over here we've got, how would we write this? We would write it like this, A1. Okay, so we can put here a mapping. There's a mapping that takes us from here to here. We'll call it I for injection. How does this work? Well, it just says that I of any A, integer A, equals A1, like that. Okay, that's good. And then we've got a B here. And of course over here, there must be a B1 Okay, so the first thing that we need to make sure, and this is part of it being an isomorphism, is that if we add up A and B and then go across to over here to what A plus B is over here, it must be the same as going over to here, and then adding these two. So let's put this as the first thing that we need to check, is that IA plus B has to equal IA plus IB for all AB that are integers. So it has to be for all of them. Otherwise, you can't really call it embedding if that rule's not obeyed. We also need, so just to go back to that. Oh, in fact, I'll do this one a bit more detail. Here's A times B, and over here is AB1. That's the fraction, essentially AB divided by 1, AB on 1. So once again, it's the same sort of argument that if we start with A and B, go to work out what AB is in the integers, go across to here, this is the endpoint. Well, it must be the same as going across to here from, oh, sorry, I've got to make sure I don't point because the pointer won't show up. Let me just use dots. So if we start here, if we go from here to here, and then if we go across using the mapping to here, well, that must be the same as going from here across to here, and then from here across to here. And then once we're in here, multiplying this one by this one to get this one. So really it's just saying that to make sense, it doesn't matter which way you go from A and B integers to AB over 1, which is the fraction. It doesn't matter which way you go, you must get to the same result. So let's just write that up. That's another condition that's important if we want to say that it's a sort of a embedding for all. This must be for all AB that are integers. This must apply. So that's one thing that's important. What's another thing that's important? Another thing that's important is that we can't have a situation where, let's do it down here, where we have, let's go for red. So we have C here and D here. We don't really allow a situation where this here is, let me just rub out this bit now. This is sort of C1, like that. So we can't have a situation where I'm going to draw the mapping in right now. This mapping goes to there, and this mapping goes to the same point. You can't have two integers mapping to the one fraction, which sounds obvious when I say it that way. So the way we would express that is that if A equals B, then no, sorry, other way around. Let's just say that if IA, if IA equals IB, then we must be able to conclude that A equals B. And this is for all A and B that are integers. So that's another aspect that's very important in terms of this embedding or containment or inclusion working properly. And then the final thing that we need to do is that we need to make sure that if we go over here, and this is obvious with the fractions, that if we've got some general fraction, call it EF, well, we must mathematically satisfy ourselves that we can always get, every fraction can be got from two of these. In other words, there's an E here and an F here, which is sort of obvious when you talk about it in terms of fractions and integers. But once again, there's a short mathematical proof of that as well. So that would be saying for all I'll just say EF, that's good enough. For all EF that are elements of a set of fractions, there exists E and F in the integers such that EF, something like this. If you're really interested in this, I'll find it up. But the basic concept is that every element here can be created from two elements here. That's also important. We can't have a situation where there's a fraction that we can't. I mean, if there was a fraction that we couldn't create from two integers, well, then we don't have an embedding in the mathematical sense of the word. Okay, so I think that's all I want to do here. Sort of a high level picture of this step 4, but I think it'll sort of point you down the right track of what you need to show. And I haven't got too involved in the really nitty gritty that you need to really do this rigorously. So I hope that's helped you. If you've got any questions on this, let me know, or any other aspect of mathematics. If I think I can help you, I certainly will.